I'm going to solve these questions with you. This is chapter 19. Okay. Some of it is chapter 19, some of the half of. No, no. It's both. Yeah. You'll have a lot of questions that comes later. Okay. Right. There are lots of statement question also. Electric charges and magnetic poles have many similarities, but one difference is. What is the difference? The striking difference. There's one difference. For example, if I take the number A, opposite magnetic poles repel, opposite charges repel, opposite charges attract. So opposite poles repel, also attract. Opposite pole, north pole and the south pole will attract. North pole and north pole will repel. So it is like the charges. So that is not the correct one. What is special about the magnets is, magnet have bar magnet, north pole and the south pole. Can I cut it into half and one become north pole only, other one becomes south pole only? No. Where you cut it, again it will form the pole, north and south, south and north. Okay, so it will never happen. So that is the difference. That's the difference between charges and magnetic pole. Yeah, isolated, it cannot be isolated. Magnetic poles cannot be isolated, but charges can be isolated. So that's the difference. So that's what is the question is asking. Okay, so the answer is this. 2. The term magnetic declination. Remember what this is? Magnetic declination? Well, the answer is there, but I hope you remember it. So you take a compass, the compass will point, we hope it will point in the North Pole, the geographic North Pole, but it's not so. It is actually pointing to the magnetic south actually, right? So that's a difference. The difference between the true north and the magnetic, the one from the magnet, a magnetic north, is called the magnetic declination. So you should know this definition. With this, there is another term which come in the same time, dip angle. Do you remember what it means? So it's another concept that you are supposed to remember. Dip angle. What is dip angle? Dip angle, the compass will point in the horizontal component of the magnetic field because it cannot go down. No way, it cannot go down because it's how it is kept. There's no freedom to go like that. But suppose you have a compass which can, the needle can rotate in any direction. It will, if you check it here in Riyadh, it will go down a bit. So what is dip angle? Dip angle is the angle between the magnetic field direction and the horizontal. So that is another one you are supposed to remember. Number 3. Now we come. So really, there will be a lot of questions, and sometimes the question students find difficult is to get the direction. Magnitude you will calculate, the formula if you can pick them, but the direction, yeah, well, so we have a question here to find the direction. An electron. What is an electron? Is a negative charge or positive charge? It's a negative charge. Electron is a charge and it is negatively charged. It has moving, that means it has a velocity in the, let me use red for the velocity. It has a velocity in the northeast direction. I hope you understand these directions. These are all horizontal directions. North, is it up? No, because I am showing it vertically, but these are all horizontal directions. They are all horizontal direction. So northeast may be like this way, that means east will be that way, and the west will be my left hand, and behind me will be south. If I am looking at north, my right hand direction will be east. My left hand direction will be west. My back will be south if I am looking at north. Okay, so that's. Then, what do you mean by northeast? NE mean northeast. Northeast means it's exactly between north and east, 45 degrees to both. Okay. Now, so if this is the north-south, where is up and where is down? North is not up. North is all, horizontal direction. If this is north, north cannot be up. It must be horizontal direction. North, south, east, west are all horizontal direction. They are never up. Up is this. Down is that. So here, what is up? Out of the page is up. You know how to put out of the page? This is the symbol for out of the page. Down will be into the page. What is the symbol for into the page? Like this. Arrow has point, right? So arrow coming out, it will be out of the page. And behind you have something like a cross, so that's why the cross. So please know how to do that. Okay. Now, that is the velocity, and he says this is moving in a uniform magnetic field directed east. So we have a magnetic field. Let me use green for the magnetic field. The direction of the magnetic field is east. So we know the direction of the velocity and we know the direction of the magnetic field. Question is, find the magnetic force on the charged particle. What is the equation? The magnetic force is given by this vector equation, which gives both direction as well as the magnitude. So the magnitude is easy. Q VB become V cross B become VB sine theta. So that gives the magnitude. But here the question is not about the magnitude, but about the direction of the magnetic force. How would you find the direction? Right hand rule. Somebody help me. What do you do? Okay, yeah, okay, you're right, okay. Say, let me go slowly, okay. Say velocity, right, let me take the pen as velocity. I will use the remote as my magnetic field. So this is making a plane, right? So you take your right hand, stretch the fingers in the direction of the first vector, which is V. It is important, okay? V is the velocity. So you put it in the direction of the velocity and try to curl your fingers towards the magnetic field. You have to have it, you should face the, keep the palm so that you should be able to curl in this plane, VB plane. If you keep like that, can you curl towards B? No. If you, let's say if you keep, what other, you cannot, right? If you keep like that, you cannot. So you can keep this way, you can. Right? If you keep this way, you're going to curl. It must be, the curling must be done in this plane. If I say the screen's plane. If you keep like this, starting from V, you need to go to the B. So that will be big angle. If you keep like that, in the direction of V, you're reaching B through a small angle. So that's what you should do. You should reach B from V in the plane that is defined by V and B through the small angle. Then look at the thumb. Thumb is pointing in. So the answer is down. Why the answer is up? Did he make a mistake? This is the direction of V cross B. We found the direction of V cross B to down into the board. But this is an electron. Electron is negatively charged. That will flip the direction, then the direction of the magnetic force will be depend also on the sign of the charge. So we get it, V cross B is down, but there is a negative in front of it that will make it positive. Okay, right. So we did that. Let me go to the next. Here, only the magnitude. So that should be easy. Can you read this picture? What is the plane of the board? Is it XY plane? What plane is the board? This is what axis? Y axis. This is Z axis. So the board is YZ plane, right? That's how. The screen is YZ plane. And where is the X axis? This one, right? That is coming out of the board. X axis is the one that is coming out of the board. But I cannot draw something coming out of the board, so I have to draw it like that. I have no choice. But you understand, right? So we have a proton. Proton is what? Positively charged. Charged particle, positive. And it has a velocity this, so that is V. Moving along the x-axis. So this proton, it's not electron, plus C means proton. This proton is going in the positive x-axis. That means actually coming to you, right? From the board, it is coming like that. That is the x-axis, positive x-axis. Right. So now you understand this. Now I cannot do it here, I cannot make a projection here. So the only way is I can show it like that. So it is shown with the red arrow. The velocity is shown with the red arrow. It is coming out towards you. And it is moving in a magnetic field. This is the magnetic field, which has a magnitude of 2 Tesla. And where is it? It's shown by this green arrow. It is in a horizontal plane. Which plane is the magnetic field? Is the plane XY plane. Okay, and making an angle of theta equal to 40 degrees. So let me show it with my pencil. So if this is my pen is the velocity, how would if I take the remote as my magnetic field, do you know how it is? It's like this. Okay, it is in the plane made by, what is this plane? X and Y, XY plane. Okay, XY plane. And the angle between B and V is 40 degrees. So he says B makes an angle of 40 degrees with the x-axis, but x-axis happens to be also the direction of the velocity. So the angle between velocity and the magnetic field is 40 degrees. Okay, right. That's it. We have everything we need to calculate the magnitude of the magnetic force, initial. Okay, then it will change later. What is the equation? This is the vector equation. But I need the magnitude, so the magnitude will be Q V B sine theta. Do we have everything we need to find the force? Is Q given? Yes. Velocity given? Yes. Magnetic field given? Yes. Theta given? Yes. All you have to do is to just substitute and get the answer. All right. Number 5. The path of a charged particle moving with velocity vector making an angle of 90 degrees to a uniform magnetic field is a circle. Because, the magnetic force will always be perpendicular to the velocity, magnetic field. So, if a particle is having a velocity v, let's say this magnetic field is into the board. So this is having a velocity like that. This velocity is perpendicular to the magnetic field, and the magnetic force will be perpendicular to both. So if I apply, the magnetic force will be like this. So this particle is acted upon by a perpendicular force to the velocity, so it will change its direction. So before the particle has a velocity to the right, now it will deflect upward because the force is pushing it this way. Then magnitude will not change. Then again it will be deflected like that. Again it will come here and it will be like that. So what happened? It will start describing a circular path. The magnetic force is always perpendicular at any instant. The force is always perpendicular to the velocity. So you know what happened, because it will be a circular path, because the tangent to the path is the velocity, and perpendicular to the tangent will be the radial direction to the center of the circle. So it will start describing a circle. So if I want to summarize it, when a charged particle has a velocity only perpendicular to the magnetic field, it will describe a circular path. So that's why the answer is circle. What if it has a component in both? It has a perpendicular component, also a component parallel to the magnetic field. It will be a helix. So while describing the circular path, okay, like this, so depending on the direction, okay, it also, let's say it has a velocity parallel to the magnetic field, it has to do both. What happened then? While describing the circle, it will also move in the parallel to the magnetic field. So it will become a circle plus straight line. It will be a helix. Okay, so that is this one, helix. But that's not the answer. Okay, so if the theta is equal to 90, that is the theta between velocity and it will be a circle. If theta is less than 90, it will be a helix. When theta equal to 0, it will not change. There will be no force. If the magnetic field and the velocity is in the same direction, or anti-parallel or parallel, then there will be no magnetic force. It will go as usual. Whatever the velocity it has, it will continue with the same velocity. Okay. Number 6. A proton having a speed of 3 into 10 to the power 6 So this is a proton, so positive charge, it has a speed this much in a direction perpendicular to a uniform magnetic field. It will describe a circle, right? We know that. And they say it describes a circle of this radius of the circle is given. What is the magnetic field? What is the magnitude of the magnetic field? Now you should remember the equation. If you don't remember, it will be in the formula sheet, something called the cyclotron equation. If something moves perpendicular to a magnetic field, it will start describing a circle. We can even derive it, just let me derive it quickly. You apply the Newton's second law, which is force is equal to mass into acceleration. Since moving in a circle, acceleration will be the centripetal acceleration, and the force you put the magnetic force. Since it's perpendicular, sin theta is 1, mv squared over r. 1v cancel with 1v. When you take this, you get this relationship for the radius of the path described by this charged particle. So that's it. It's a matter of just substituting thing into this and finding the unknown. The unknown is obviously asking for the magnetic field. It looks like this is the unknown. Everything else is given. R is given, substitute. Mass of the proton is given, substitute. Charge of the proton is given, substitute. Speed is given. Okay, everything else is given except the magnetic field, so you can find the answer. Okay, we'll go to the next. Number 7. The direction of the force on a current carrying wire in a magnetic field. So you know the force is perpendicular to both the velocity if it is charged particle. Now are we talking about the charged particle? No, we are talking about a current carrying wire. So the equation is now different because now you write it in terms of the length of the current carrying wire, L cross B, L is the length, and the current I. This is the equation. So the magnetic force will be perpendicular to both the L. L has a direction, which is the direction of the just coming here so that can say that I am present. No, you are not. So the force is perpendicular to both the current and the magnetic field. So the answer is D. All the other choices are wrong. Number 8. We have a rectangular wire loop with n turns. So the purple color thing is the wire loop, but it doesn't have just one loop, it has many loops, n turns. We didn't say what it is. Maybe that is the question, to find the number of turns. Okay, that's the question. It has a length and width given like that. That means I can find the area. It's a rectangle, so length multiplied by width will be the area. This loop is kept in external magnetic field B, and here it's shown in this green arrow. And we send a current of 7 milliamperes in that loop. And when you do that, I mean, any current carrying loop will have a magnetic moment. It is found to have this magnetic moment. Question is to find N. So the question doesn't have anything to do with the magnetic field. The moment we have a current carrying loop, it has a magnetic moment. Any current carrying loop will have a magnetic moment. It is a magnet, so it has a magnetic moment. What is the equation for the magnetic moment? Yeah, that is the symbol for magnetic moment. So if you have a current carrying loop, how do you calculate the magnetic moment? Equal to that's it. Okay, if you have a current carrying loop, all you need is how many loops we have, what is the current through it, and what is the area of that. Then you can get the magnitude of the magnetic moment. Substitute. N is given, no, that mu is given, I is given, A is given. Find the number of loops. So it's working backward. So you substitute for 0.175. N is the unknown. I is equal to 0.1. So no, 7 milliamperes, right? So milliamperes means 7 10 to the minus 3, and area is 2 into 2.5 L into W. Area for rectangle is length multiplied by the width. So you just solve for N, you get the answer for N. All right, let me ask another question here. So you found mu is a vector, magnetic moment is a vector. How do you define the direction of mu? It is perpendicular to the plane of the loop. So if this is the loop, This is the plane defined by the loop. So it will be perpendicular to it. But you have two choices, perpendicular this way or perpendicular to my direction or towards you. How do you know that? So tell me here, this is x, this is y, z is outward. So which direction is the magnetic moment? The x direction, y direction, or z direction? The magnetic moment is perpendicular to the plane. Z. Is it positive z or negative z? Z is the one coming out, right? This is in this plane. Is it positive z or negative z? Huh? Sorry? Yeah, that is what I'm asking. What is the sign of the mu? That is the question. I am telling you the way we define is perpendicular to the plane. So it could be plus z or negative z. Which one is the correct one? Why? Now we are defining, we say you curl your fingers in the direction, curl your right hand, okay, in the direction of the current. So it is like this. Look at the direction of current. It is outward. If it is, say, counterclockwise, it is outward. Clockwise, it will be inward. So that's how you decide between the two directions. Okay, we define it so. Okay, it is perpendicular, but when you say perpendicular, there is ambiguity. There are two directions to choose from. How do you choose it? By looking at the flow of the current. Yeah, just curl your fingers and see whether it is this way or the other way. Right hand, okay, not the left hand. Right, so when you do that, you get n is equal to 5. Let me now go to the next question. Number 9. It's the same thing. Actually, one question broken into two, if you can say that. Here again, we are using the same thing. He is giving the magnetic moment like before. And he is giving the what, a torque. And ask him for the magnetic field. He's saying we keep in this current carrying loop in a magnetic field. We don't know what it is. When you do that, it starts rotating because it is experiencing a torque. And the torque is given to you. And ask him for the magnetic field. Now, what you should remember is when we have a current carrying loop or a mu, kept it in a magnetic field, it will experience a torque. We have an equation for that. Do you know that equation? Don't say micro, mu. Okay. Mu. There's a letter, Greek letter mu, but as a prefix, we call it micro in a SI unit. Okay, but here you call it. This is the vector equation. It's complete. If you want the magnitude, it will be. He's asking for the magnitude. Yeah, good. Okay, right. No. Yeah, okay. He's asking for the magnitude, so we have to have everything be magnitude of not. Yeah. Can I undo? Let me write it again. So torque is equal to mu cross b. Since we are talking about magnitude, so the magnitude will be mu b sine theta. This is given, this is given, this is it given? Yeah. The angle, what is theta here? Angle between mu and b. Mu is positive z direction and b, okay, theta is given. Okay. So all you have to do is to just substitute and find the unknown. Easy, right? So shall I put the value so you can check, you make sure you get this answer. Tau is equal to 1.0 0.10. Mu is equal to 0.175. And B is equal, that is the unknown. And sine theta is equal to 75. So solve this, we'll get the answer. Number 10. A long straight wire going through the origin is carrying a current I in the positive Z direction, shown red in the figure. What at the point P on the x-axis, what's the direction of the magnetic field due to this current carrying wire? Okay, let me explain this graph, okay, because when I say something, you should be able to understand. What is the plane of this board? Is it XY, YZ? XY. Plane of the board is XY. Are you all clear with me? The plane of the board is XY. And Z is coming towards you. So that is the only. So you can visualize it, right? 3D visualization. This is very important. Okay, you should be able to do that. Right, now everything is clear. So the current carrying wire, if I take my pen, I'm holding in my hand, it is coming towards you. This is the wire that carries the current. So the current is coming towards you. Okay, right. But this is the only way I can draw it. Okay, so it's not a 3D. Okay, so 2D we can. Now, what kind of magnetic field? If you have a current carrying wire, it's like a magnet. How do you know what kind of magnetic field we have? I taught you in the lectures, right? It will be circles. The magnetic field lines will be circles around this wire. How do you get the direction of that circle? Which direction is the magnetic field is? Right hand rule, well, right hand number 2. Put your finger in the direction of the current. It's called the right hand number 2. And right hand, okay? Look at the curling, bending of your fingers. It is going, from your point of view, it is going counterclockwise, right? So it is like this. How do I know experimentally? You take a compass. Compass will point in the direction of the magnetic field. So when you take the compass here, what direction will it turn? It will turn like this, right? Because that's the circle. When you keep it here, it will be like this. If I keep it here, it will be upward. So you get the point? Now you know the answer. So, for example, if you draw a point here, there is a point here in my where I am pointing with my finger. So if I keep a compass here, the compass will point down. So the magnetic field at this point where I have drawn this X, it will be down. At the point P, it will be up. Okay, so that's the up mean positive Y direction. It's clear? Shall I ask you another additional question? Let me choose Q, point Q. What is the magnetic field direction at the point Q? Very good. Negative. All right. Let me choose another one between these two. Here, say R. It will be tangent to the circle, right? If you, here, it will be tangent to the circle. Here, it will be down. Here, what is the, at this point? Up. Positive X. Here, it will be something like this. Okay. And here, it will be tangent to the circle and so on. So I hope you get the point. Right. So let's go to the next question. What we have here is two wires. I'll use wire 1. I will use the blue pen. So this is the wire 1. So it carries a current I1. Okay. Then we have a wire 2 perpendicular to that, kept perpendicular to that. It carries a current I2 but downward. The question is, which of the following regions A, B? A is the first quadrant, if you call it a X and Y axis kind of. You understand, region A is here. This is the region B, region C, region D. In which of the following region, A, B, C, D, the magnetic fields from both currents points into the page? Yeah. Okay, I don't know how much you understood, but let me do for this region. I'm going to go to the region A. In the region A, I'm going to find what is the direction of the magnetic field from wire 1. Can you tell me the answer? This is the wire 1. Okay, and it will be circles, right? It will be circles around this wire. The magnetic field will be a circle. So in this, okay, this is the plane I'm talking about. This is my screen. This is the screen plane. So you put your finger, then it is coming anywhere up above this wire. The magnetic field will be out of the board. Is that clear? Any region above the wire, the magnetic field will be from the wire 1 will be out of the board. Any region below the wire, the magnetic field will be into the board. Okay, right. So I will use my blue pen and I will show the magnetic field direction in the area A as, what did I say? Out of the board, right? You know how to put the out of the board. This is out of the board. In this region also, out of the board for the blue. What about this region? Into the board. Here also, into the board. Is that clear? Okay. Now let's go to the red wire. Tell me. Let me start with A. Oh, right and left. Because right side it will be one direction, left side of the red wire will be in another direction. Tell me. The circle wire is going down. The circles will be like this. On the left side it will be, right side it will be out. So what did you say? On the right side it will be out. Left side it will be, this is the wire going down. So right side, on this plane, in this plane, right side, your right side, it will be out. On your left side, it will be in. Okay. Oh, other way around. Other way around. So I am saying the right thing but drawing the wrong symbol. So on your right side, it will be out. Out mean dot. Out mean dot. That's the symbol for out. On your left side, it will be in.
It's not like this way.
Look, this wire is going in. I'm looking at wire number 2, not wire number 2 is going down. On your right side, it will be out. On your left side, it will be in. So I'm using the red for the wire number 2. So on the right side of the wire number 2, it will be out. On the right, left, confused. Okay. On the right side and your left side, it will be in. Okay, right. Now you know the answer. In which region we have both, from both wires, magnetic field to be out? In out. Into the page. Sorry, into the page. Yeah, into the question is into the page. Okay. So the answer is C. Okay. So if you understand this question, then you understand how to get the magnetic field from a current carrying wire. They are circles. Okay, they are circles. All right. I think the next question is, yeah, another question. Yeah, that. Right. This is the last question chapter. Right. This one you should answer without me helping you. Don't give the answer that is already there. You have to explain the answer. Is it a long wire now? No. It is a loop, circular loop. So we have two wires, which are circular wires, and there is a current I1 in the big circle and current I2 in the small circle. The question is about the magnetic field at the center of the circle. It's telling the magnetic field is 0. How come it is 0? Because from one wire, the magnetic field cancels the magnetic field from the other wire. Now, what you need to know is an equation. Do you know the correct equation to use? What is the magnetic field at the center of the wire from the circular loop? We have an equation in the formula sheet. Magnetic field is equal to N mu divided by I divided by 2R. This is the equation. Once you know the correct equation, there's no pi, okay? The pi is for long straight wire. For a circular wire, the magnetic field at the center is this. Okay, right. Now, both of these loops will have a magnetic field at the center which will be perpendicular to the board, right? If it is clockwise, it will be in. If it is counterclockwise, it will be out. So you can say I1 will give you a magnetic field which is into the board. So into the board will take as negative field, okay? So into the board we'll put negative, out of the board we'll put positive. So B1, that is the magnetic field from the current I1, will be equal to N, let me call it N1, I'll put the substitution at the end. N1 mu 0 I1 divided by 2 R1. And I know that it is into the board, so I put a negative sign. They are all magnitude, so I have to put a negative sign, so I get the correct direction into the board. B2 will be, it will be plus, right? We already know it is plus. And 2 mu 0 I2 divided by 2 R2. Then we know the net field is B1 plus B2 is equal to 0. That means this is equal to this. The magnitudes are equal. In other words, I can write B1 plus B2 is equal to 0. That is the condition given. Net field is 0. That means N1 mu 0 I1 divided by 2R1 is equal to N2 mu 0 I2 divided by 2 R2. That's it. In this equation, the only unknown is mu 0 will cancel anyway. You don't have to substitute that even. Only unknown is R2. Everything else is given. I1 is given. Let me. Also he is saying I1 is equal to I2. He is telling in the question I1 is, it's not given, but he is telling it is equal. Okay. Otherwise, can you cancel it? No. If the question doesn't say such thing, you cannot cancel it. The question says I1 is equal to I2. So finally we get N1 divided by 2R1 is equal to N2 divided by 2R2. Everything is given except what? Except R2. So substitute for what is given and we can find the value of R2. Okay, I will stop. See you in the next class.